The world is full of complex problems, from designing an education system to a citywide public transportation network. This morning, I got the train into the city, but now I need to get to Shoal's offices on Angus Street, and I think I'm going to get a bus or a tram, but I'll figure it out. Designing something like a transportation system takes systems thinking. It's no coincidence that Adelaide Station is the hub for this place, and there's plenty of bus stops, a couple of tram stops, so my options are open. And these systems line up pretty well when they're running on time. Designing something such as a citywide public transportation network is a complex problem. I mean, you can buy a bus and you can buy a tram, but you can't really buy the network. It takes a lot of processes and methods to get that right. It requires a consideration of all the various stakeholders, government, individual operating companies, to make it work properly. Systems engineering provides a structured approach from which you can look at these problems and better understand what they are and enable a better holistic design. These problems aren't just technical. There are a host of social and cultural problems that are just as complex, such as global warming or the massive plastic island that's in our ocean. Another well-known example of systems engineering in practice are the NASA Apollo missions. NASA engineers had to consider the launcher requirements, the amount of payload they could take, or even the potential landing sites before starting to design a solution. They had to look at the hardware and software that was available, the time-evolving budget, and even reassess the scientific and engineering needs of the mission. And they had to look at all these things at the same time. Systems engineering presents a series of approaches and methodologies through which we can better understand these problems. There have been a multitude of technological advancements, especially in the space industry recently. Companies like SpaceX and Rocket Lab are looking at using reusable rockets, and other companies are looking at alternative low-cost fuels. This is making access to space quite easy. There have even been ambitious talks of colonising Mars. But before Mars, what about the Moon? We currently have the technology to be able to do that. Current estimates from NASA and the private sector say it would cost about $20 to $40 billion and take about 10 years. Which is about the cost of the International Space Station. Perhaps that would be a good stepping stone to build technologies and lay the foundation for us to travel to other planets in the future. It might look something like this. So let's have a look at a problem. We're a private company interested in building a moon habitat. Our team has been tasked with developing a sample return capability. That is, once our habitat is established, how might we go and collect samples from the surface of the moon? Let's head back to the office and we can apply some systems engineering to this. Economics and costing aside, our team has been tasked to design a sample return capability. That is, once our moon base is set up on Mars, how will we then collect samples and return them back to the habitat? So that's all we've got really. We've got this vague statement of a sample return capability, and now we have to go and design it. So this problem requires systems thinking concepts. So where do we even start? Well, a good place is the Systems Engineering Vee, or the design lifecycle. Now this is a process all products go through, from their conceptual design to their operation in their environment. So you can see at the start there's the problem definition. So a good design process begins with understanding what the problem actually is. And then after that you move into your concept. And after you've got a concept, you can then start to flesh out what the system needs to do or to look like, and eventually get to your requirements. Your requirements are real specific. And that's typically what a company will grab and say, all right, I'm going to build this. And that's when you get into your design and build phase. So you're designing the details of your capability and actually building it. And then you start to move up the other side of the V, where you're verifying and validating what you've built against your system requirements and also against the actual problem. So is what you've built fit for what you conceptualized? And is it also fit for what the problem actually was? Did you actually fix the problem? In this case, we'll go through the first few sections of this process. We've kind of understood the problem a little bit, but we'll work on that some more and then also move into looking at the conceptual design. How do we take this problem, that is, design a sample return capability, into something conceptual? Usually this involves quite a lot of client interaction, lots of stakeholder workshops, with not just the client, but anyone who will interface with the system in the future. What do they need from this system? What does the rest of the habitat designers think about our sample return capability? What does the government think about our sample return capability? What do the scientists who will be analysing the samples at the habitat or on Earth need from this system? All the way down to the operator that will be working the machinery. What do they need from this system? And including these considerations really early in the design is critical to designing a holistic, well-considered and successful design. So through these conversations, you get a better insight into what the system needs to do. So you can start to develop what's called functions. So in our case, for the sample return capability, a function might be that it is able to collect. Quite simple, it should be able to collect samples somehow. Another requirement could be that it should be able to move around the terrain. Perhaps another one is that it should be able to navigate and avoid obstacles. And so the list goes on. You could have hundreds of functions for your system, and you start to tease these out when you start to talk to people about what they need from the system. Another thing that will fall out of these conversations are the components of the system. So in our case, we might have a collection system that's responsible for picking up the sample off the ground. Or we might even have a transportation system that carries the sample or that picks the sample up from the ground. Or a control system that coordinates from the computer chip how the system will move. These are all classified as components. Another thing you might discuss are items in the system. So these are things like the sample itself, or even a piece of information like the command that goes from the computer chip to the wheel, if there is a wheel. So now we've got a bunch of information. We've taken this ill-posed statement, we've talked to our stakeholders and our clients, and we've got these functions that the system needs to perform and the things that it needs to have. So how can we begin to take this into a concept? So let's start with this diagram here. Now this is going to show the activities that will be performed by the system when it's in operation. So let's have a scenario where the system needs to go, move towards a sample, encounter an obstacle, navigate around the obstacle, collect the sample, and return home. So these functions are shown on the diagram. You can see here how it's the transportation system that handles the moving piece, but then the collection system handles the collection piece, and the control system handles managing the information between the two. This is just an example of 3 components. There could be many, many more. What you'll also see on the diagram is the information items that are passed between the systems. So here's how all of these things that we've discussed before interact. So what we've developed here is a concept of the system of how it will behave when it's in action. So we can use further scenarios to refine this even more. So another scenario might be the system endeavours to go and collect a sample, but it runs out of power. Now this might mean the astronaut runs out of food when he goes to pick up a rock, or it might mean the rover can't see the sun, so can't power itself. It doesn't matter which one it is at this conceptual level, it could be either. So we can identify here that perhaps the system needs a recovery component, and we can add that in the diagram. And then perhaps as part of that, it needs to be able to contact the habitat or send its location. What you can see here is we've added 2 new functions and a new component to the system concept. And this is how you'd start to flesh out your system properly. You can add more and more scenarios of how you think it will operate in its environment and begin to add functions and requirements. Doing this scenario-based analysis is just one way of getting your requirements. The International Council on Systems Engineering, or INCOSE, do a great handbook that discusses multiple ways of doing this, so see that for further reference. So what we've got here is our concept of what the system looks like, and we've used the scenarios to develop this. But what's important to note is that in no way does it specify what the system actually is. So for instance, the transportation system that needs to move and navigate, it could be wheels and a rover, it could be an astronaut in a suit, or it could be a T-Rex. As long as it can perform those functions, it doesn't actually matter. Now we used a series of fairly high-level scenarios to develop this, but we can start to make those scenarios a bit more detailed to make our concept a bit more detailed. So for instance, one of the scenarios might be that it needs to collect a sample that weighs 5 kilos that's located 15 kilometers away from the habitat. Now you can start to see what your system will have to look like. If this is a requirement of the system and this is one of the scenarios, then perhaps an astronaut in a suit that has to walk for 2 hours is not the best solution. Perhaps a rover or a balloon drone would work. Who knows, but it's not going to be a human. So you can start to see how it's going to take shape. And that will enable you to develop even more scenarios, such as it loses contact with the sun. So now you've got a power system requirement, but you know a little bit more about what your power system looks like. So after this process, you'll end up with a set of detailed specifications to which you can design your system to. Options analysis and trade-off studies and a technology review. But you can start to actually build something tangible now that you have your concept defined, you've considered your stakeholders, considered the needs of the mission and the requirements of the system. Now this is at the bottom of the V, but we start to build the components. If it's a rover we're designing, we might start to build the power system, and then the wheels, and then the camera, and then the claw to collect the samples, if that's what it is. And after that, you move towards the assembly stage, where you start to put all the components together. Now in your concept, you've already looked at how they all interface with each other and what the requirements are for that. So you'll be making use of that thinking that's already been done. Now after you've got your assembled integrated system, you can then start to do some verification. So check that your system that you've built is what you actually specified in your conceptual design, and that it actually performs all the functions that you needed it to perform. And after this, you can move to validation, where you check to make sure that your system actually solves the problem. Have you designed something that's fit for purpose? With these set of detailed requirements, you can now start to build your system and build something tangible. In the next video, we'll talk a little bit more about how to take these requirements into the build phase and further after that.